Hello everybody. In this video, we are going to be doing 6-1, but we're also going to be doing part of 6-4. So what we'll do today is we will look at key features of something called an exponential and logarithmic. That's an R right there, and logarithmic functions. So we'll talk about what is an exponential and also what is a log function. We'll identify the key features of exponential and log functions, and then we'll transform those parent functions using the transformation rules that we've done all year. So first we're going to start in 6-1. We'll look at the exponential functions. And it's important to look at functions a couple different ways. We want to look at them with a formula. We want to see what that formula does to a table, and then we'll graph all of these points. So whenever you're looking at exponential formulas, the formula for an exponential function, you can tell it's an exponential function by the formula because there is an x in the exponent spot. It could be x, it could be x minus 2, x plus 3, 3x, 4x, but as long as there's an x in the exponent spot, then we call it exponential. Now let's look at what would happen in the table. If the x is 4, then y, which is the same as f of x, or we can think of it as being the same, y would be 2 to whatever x is. So if x is 4, y would be 2 to the 4th, which is 16. If x is 3, y would be 2 to the 3rd, 8. If x is 2, y would be 2 squared, and 2 squared is 4. 2 to the 1st is 2. 2 to the 0 power is 1. 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. And 2 to the negative 3 is 1/8. So now let's plot all of these points. So I plot these points, and I see that I have this nice curve that looks like it's really close to the x-axis. It actually never goes below the x-axis because there's nothing that x could be that would make y be a negative number. So the y values get really close to the x-axis, but they never touch 0. If they never touch 0, then that means that we have a horizontal asymptote at the equation or at the line y equals 0. So right here, horizontal asymptote. At y equals 0. We don't have any vertical asymptotes because this graph will go forever and ever to the left. It'll go forever and ever to the right. So no vertical asymptotes. What else do we notice? It looks like that starts off really slow, like it grows. The y values get bigger really slowly, and then they start to jump really fast. So you may have heard the expression, there's exponential growth, or this grows exponentially, and it's based on this function. We see an exponential growth because there is all from one x value to the next. As x increases, the y values jump up higher really, really fast. So if we start identifying things like domain, range, intercepts, and asymptotes, and then behavior, our domain, since there are no vertical asymptotes and no holes, our domain is negative infinity to positive infinity. The range is affected because the graph does not go below the x-axis. So my range goes from 0, from y equals 0 until infinity. So range would be from 0 to infinity, parentheses on the infinity, parentheses on 0 because the graph never touches the 0. It looks like it's getting really close, but it never actually touches. So domain, range, intercepts. All right, let's see the y-intercept. The y-intercept is whenever the x is 0. So when x is 0, y is 1. And then asymptotes, there's an asymptote at y equals 0. And in behavior, so what's happening on the right side and what is happening on the left side. Well, as on the left side, which is what happens as the x values approach negative infinity. So as the x values get really small, the y values approach 0 because they get really close to the x-axis. Then on the right side, as the x values approach positive infinity, the y values, so x values are getting really big, the y values are getting really, really big. So the y values approach infinity. So that's what we'll see on this exponential function. Now we have other exponential functions. Now here's an extra example, but it's also important to graph this one. Y equals 1/2 to the x. So instead of having a whole number raised to an x power, what happens if I have a fraction raised to the x power? So let's fill this out and see what happens. So now as we can see, if you fill out the table, plot some points, we see that we've got a similar graph with a similar curve, but it's facing the other direction. The one before started off really close to the x-axis and then grew exponentially. This one started off on the left side pretty with the high y values, and then the y values decline or decay pretty rapidly, but then when they get close to the x-axis, they start decaying or shrinking or decreasing really slowly. So, and that's going to happen anytime this number in front of the x is a fraction less than 1. So if it's in between 0 and 1, you'll see that behavior. The domain will stay the same. So our domain is still negative infinity to positive infinity. Range is still 0 to infinity. The y-intercept is still right here, 0, 1, and also I can see when x is 0, y would be 1. The asymptote is still y equals 0. And behavior on the left side this time, as the x values approach negative infinity, so on the left side, as the x value gets smaller and smaller, the y values are larger and larger. Then on the right side, as the x values get larger and larger, the y values get smaller and smaller. So if we look at our two types of exponential graphs, we'll have, and don't worry too much about the growth factor today, don't worry too much about the decay factor. What you need to know is with exponential functions, they're going to do one of two things. They're either going to grow exponentially or they're going to decay exponentially. And it all depends on this number that's being raised to the x, what that number is. So if that number is greater than 1, you'll have an exponential growth graph. If that number is less than 1, you will have an exponential decay graph. You also need to know about this number called e. E is a new constant. So in the past, you've learned about numbers like pi. Well, now we have a whole new constant called e. It was discovered by Jacob Bernoulli, and the mathematical constant is approximately 2.71828. If you look on your calculator, you'll see the e button somewhere on the left, but we will be using e a lot. And it happens whenever we're doing something called compound interest, which we'll study in the next lesson. But for right now, you just need to know that this is approximately what e is equal to. And we're going to also think, okay, well, if e is approximately 2.718, that means that this number is greater than 1. So I know that I'm going to have an exponential growth function. I can also tell without having to use my calculator whenever x is 0, because anything to the 0 power is 1. So I can also tell that I have a point at 0, 1. Since I know that it's exponential growth, and if x is 1, y would be like 2.718-ish, whatever this number is. Anything to the first power is itself. I can get a pretty rough sketch of what this exponential function is going to look like, because all exponential functions have the same shape. They're either going to grow or decay. So know that that letter E is going to come up quite a bit. So what we're going to do now is we are going to look at the inverses of these functions. So flip over to section 6.4, and we're going to look at log functions. Now, we will study log functions more in depth as we go, but for today, the only thing that you need to know about log functions, besides what they look like and how to graph them, all you need to know for today is that log functions are the inverse of exponential functions. Exponential, I can't spell today. Exponential functions. Now, what does that mean, inverse functions? Well, that means that the x and the y values are switched. We're going to use this one fact to look at the graphs of our logarithmic functions. So looking here, we have this function that says y equals log base 2 of x. And the way that you read this is you read y equals log with a base 2 of x. What does all this mean? You'll learn that later. Today, we just need to know that this is the inverse of an exponential function. And it's inverse of a specific exponential function. Do you see how this base is 2? That tells me which exponential function this log function is an inverse of. So log base 2 of x is the inverse of y equals 2 to the x power. So whatever that base is, that's what the base of the inverse of its inverse. So let me just remind you of what the table for y equals 2 to the x look like. It look like this. So if I'm going to graph the inverse, then I'm going to switch the x and the y. So I'll switch the x and the y. So if the function y equals 2 to the x had a point at negative 3, 1/8, then x would be 1/8 and y would be negative 3. I'm literally going to switch every single one of these. And I'm going to graph them. 2, 8, 3, and then I'm looking down here, 16, 4. Now I'm going to plot all of these points and see what it looks like. So here's what I'm looking at. I see, instead of a graph that starts slow and grows quickly, I have one that kind of grows quickly and then starts to level out towards the end. So this is what we call a logarithmic function, but we say, for shorthand, we say log base 2. All right, so I'm also noticing that instead of a horizontal asymptote, the log function has a vertical asymptote at right here at the x-axis, which is the line x equals 0. So vertical asymptote at x equals 0. And then what are the domain, range, x-intercept? So domain would be 0 to infinity, because there's no graph on the left side of the x-axis, and then 0 to infinity. The range, negative infinity to infinity. Now, if you look back, you'll see that since the x and the y are switched for 2 to the x and log base 2 of x, the domain and range are also switched as well. The x-intercept would be whenever y is 0, what is x? So here's the x-intercept. Here's the x-intercept. So at 1, 0. And what else do we need to find? We found the asymptote already. And behavior. Now this graph is interesting because there's not really a left part, so we have to start where the vertical asymptote is. So at x equals 0, so we can say, so we can say as the x values approach 0, from the left actually, the y values approach negative infinity. So that's saying as we get closer and closer to that vertical asymptote, the y values are going down, they're decreasing. And then as the x values approach infinity, as the x values get larger and larger and larger, the y values are getting bigger. Not as fast as the exponential function, but still eventually infinity. So we'll put infinity right there. Now let's see what else we have. Now we also have this function, whoa, and it looks like in, but this is really an L. So make sure you take a note of that. This is an L. So you might want to write y equals Ln of x. And so Ln is the natural log. And the natural log function is a special function. It's reserved only for a base of e. And so it's only for the base of e, so you probably won't see that e written there. Actually, you almost never see the base e written there, but it's understood. So if you see this Ln, that means natural log, and the base is always e. So that might sound like, what is she talking about? Well, for today, all you need to know is that means natural log. The base is e, and it is the inverse of y equals e to the x power. So let's see, this is the inverse. So if I want to graph y equals e natural log of x, I just take my e to the x function, switch all the x's and y's, and sketch a graph. And that's all you'll need to do with the natural log function today. We will do more with it later, but that's what you need to know. So now that we've got our log functions, we've got our exponential functions, how do we move those functions around? How do we shift them to the left, right, up, down? How do we reflect them? It's all based on the way that the formula is set up. So first of all, we need to start with the parent function. And so with exponential functions, what you'll find is that there's actually several parent functions. So like y equals 2 to the x is a parent function. Y equals 3 to the x is another parent function. Y equals 4 to the x is another parent function. Y equals 1/2 to the x is also a parent function. So there are several different parent functions within the exponential function family. Lots of parents going on here. It all depends on the base. So notice, like, if 2 is the base, 3 is the base, 4 is the base, 1/2 is the base. So this b to the x is really going to set up your parent function. So first of all, you're going to need to identify what is the parent function. Then you'll see numbers. You might see an a in front, a plus or minus a number up here, plus or minus a number outside by itself. These are the numbers, this a, the h, and the k. Those are the numbers that are going to move the function up, down, left, or right. Sometimes you'll see this k added at the end. Sometimes they like to put it at the beginning. But here's what you need to see. If you see if you look at the equation and you see a minus h, that means your function is going to shift to the right. If you see a plus h, it will shift to the left. If you see a minus k, that function is going to go not up, it's going to go down. Plus k will mean the function will shift up. And negative a is a reflection across the x-axis. And negative x is a reflection across the y-axis. And then the A will be our vertical stretch or compression. So vertical stretch if that A is greater than 1, compression if that A is between 0 and 1. So let's look at a couple examples. Example 2, by the way, these examples are in section 6.1 because we're back in exponential functions. All right, so here we go. So I have, how do the asymptote and the intercept of the function compare to the asymptote and the intercept of the function f of x equals 5 to the x power? And right now I have 5 to the x plus 3. All right, so 5 to the x is, you can think of it as being our parent function. So I think about what this graph looks like. And then how would it compare here? 5 to the x plus 3. Well, I look at this and I see, oh, okay, it's in the exponent's place. So the thing that's in the exponent's place is the h, okay? And I have a plus h. So that means that my function is going to shift to the left 3 units. So 5 to the x, okay, so I think 5 to the x, that is a growth function. It's going to kind of look like this. I know 5 to the 0 is 1. So I know that here's a rough estimate. And then I also know it has the point when x is 1, y would be 5. So I'm just going to sketch this in 5. No, sorry, when x is 1, y is 5. And then I could substitute in more points if I want. I could substitute in 2, 3, 4, 5. But here's two key points that I want to think about. Everything, this is the parent function y equals 5 to the x. And I ask, how is everything going to compare? Well, let's see, everything is going to shift to the left 3 units. So this intercept is going to shift to the left 3 units. The asymptote, because it's a horizontal asymptote, will stay the same. And that, I just realized this says unitus. U-N-I-T-S. Okay, example, is there, nope. Here's another example. Here we have another function. How does it compare? Well, I see that there's a plus 1, and it is not in the exponent's place. It is a constant that's being added, so everything is going to be shifting up 1. So the horizontal asymptote that was right here now is going to shift up 1 unit. And then the negative is going to reflect across the x-axis. But I do need to be careful about the order that I do this in, because if I reflect and then move everything up 1, it's going to be different than if I move, it could be different than if I move up 1. Oh, I didn't need to erase that. If I move up 1 first. So how do you tell the order? You go in order of operations. So always start with the x, start here with the x, and then follow the order of operations. So there's x, 4 was raised to that x power. Then I need to reflect, because then that negative needed to happen. So first of all, I need to reflect first. So let's reflect. I'll do that in green. I'm going to reflect across the x-axis. So this point was the y-intercept. Now it's going to be down here. Okay. Then I'm going to shift everything up 1. So then this is going to move up 1. The x-intercept was here. Everything shifts up 1. And so that's what we will do. Now with log functions, now go back to section 6.4. Graphing with log functions. So we'll have our parent function, and your parent function is based on that base. So if you have y equals log base 5 of x plus 3, your parent function is going to be y equals log base 5 of x. So if you know what log base 5 of x looks like, then I could see what happens with log base 5 of x plus 3. So it works the same way. We're going to be looking for adding or subtracting inside grouping symbols, adding or subtracting outside grouping symbols, and then this a in front. So if you look at the equation and you see a negative h, that means you're going to shift that log function to the right. Positive h, you'll shift that log function to the left. Negative k down, positive k up. Negative a, reflect across the x-axis. Negative x, you reflect across the y-axis. And then that a is the vertical stretch or compression. If a is greater than 1, vertical stretch. If a is between 0 and 1, compression. So you'll have some that look like this. Example 2, describe how it would compare to the natural log of x. Remember, natural log, if I have f of x equals natural log of x, remember that base is e. So this is my parent function. So the question is, how does this compare to the parent function? And I see that there's a plus 4. Scroll back up. Notice the plus 4 is not inside parentheses, so that means it would be the k part. Sometimes that k is at the end, sometimes the k is at the beginning. And is it a plus 4? Yes, it's a plus 4. So plus 4 means that natural log of e, or natural log base e of x, is going to be shifted up 4. So everything would shift up 4 units. And then 5 times the natural log of x, that would mean the natural log function would have a vertical stretch of 5 units. So I think that ends our examples for today. We will continue our lessons in exponential and logarithmic functions. We will dive deeper. It may feel a little uncomfortable right now, but we will get there. So have a great day, and I'll see you guys next class.